Jai Hind everyone. I Prashant Tripathi, Assistant Professor at AKGEC Engineering College in Electronics and Communication Engineering Department, going to present a complex lecture on topic Multicarrier Modulation Technique. This topic is aimed for BTech students who are studying wireless and mobile communication. The content of this lecture are orthogonal frequency division multiple access, interleave division multiple access, hybrid method for multiple access scheme, and multi-carrier modulation technique. So, in this lecture, we will cover these 4 topics. First, we will discuss about orthogonal frequency division multiple access technique. So, in previous lecture, we have discussed the multiple access technique, which are frequency division multiple access technique, time division multiple access technique, and code division multiple access technique. In the purpose of multiple access technique is to provide the communication channel among different users so that we can utilize them effectively, because the individual user has very low bandwidth requirement, and if we use entire channel for a single user, then we will waste our bandwidth. And as we know that in communication, whether it is wireless or wired, the bandwidth is a primary resource. So, our purpose is to efficiently utilize the communication resources, which are channel bandwidth and power. So, multiple access techniques are designed to share the communication channel among different users so that they can be utilized efficiently. In frequency division multiple access technique, we have seen that the entire frequency range is divided into narrow frequency band, and each band is allocated to a dedicated user. In frequency division multiple access technique, the channel has full control over the allocated user. When user want to transmit some information, he or she can utilize that channel which is allotted to her. But when the user do not transmit anything, the channel is ideal and there is a wastage of channel. To solve this problem, time division multiple access techniques are used, in which the channel is shared on the time basis. If there are 4 users, user 1 will utilize first few seconds, for example, user 2 will allot next time slot, user 3 will utilize next time slot after user 2. So, in this time division multiple access technique, there was a problem of synchronization. After time division multiple access technique, code division multiple access technique is introduced, which utilized various orthogonal code to encode the user's information, and after encoding user's information, the combined information can be transmitted on a single channel. These all things we have discussed earlier. Now, the next multiple access technique is orthogonal frequency division multiple access technique. Orthogonal frequency division multiple access technique is basically a digital carrier modulation technique which extend the concept of single subcarrier modulation by utilizing multiple subcarriers over the channel. In orthogonal frequency division multiple access technique, rather than transmitting the entire information on a single carrier, it utilizes multi-subcarriers which are closely spaced and orthogonal with each other. So, in orthogonal frequency division multiple access technique, we use different subcarriers and these subcarriers are orthogonal to each other. As we compare with classical technique where single carrier was used to transmit the information, in orthogonal frequency division multiple access technique, different subcarriers are used for transmitting the information. Normally, when we use any kind of modulation to transmit wires data, the sideband after modulation, the sideband obviously is spread out like this. If we transmit a rectangular pulse, then it will spread out. So, when we transmit a sequence like 1 0 1 0, we will get waveform like this. Each waveform will spread out. Due to this spreading, the pulse will interfere each other and we will get inter-symbol interference. And due to this inter-symbol interference, we will not able to detect the transmitted sequence correctly. This is a big issue in communication. And also to demodulate the transmitted data sequence for complete demodulation. So, in such kind of transmission, we will get inter-symbol interference and we will receive the wrongly detected bit sequence. Also, in this type of transmission, we need a sharp response filter to get the exact information. Also, it is very difficult to design a sharp cutoff filter response. So, to realize such kind of filter, practical filter, when we use practical filter, we need some guard band so that the information from next bit do not appear in the previous one. And as we know that the presence of guard band is also a wastage of bandwidth. All these problems are removed in orthogonal frequency division multiple access technique. In orthogonal frequency division multiplexing, we divide each channel into narrow subcarriers. The spacing between these subcarriers are chosen such that they are orthogonal with each other, because if they are orthogonal to each other, there is a very less probability of inter-symbol interference. And to make the subcarriers orthogonal, the spacing between the carriers is reciprocal of the symbol period. This is the essential condition to make subcarriers as orthogonal. Here is I have demonstrated the example of subcarriers. 4 subcarrier channels are shown in this figure. The spacing between these subcarriers are reciprocal with the symbol period. Delta F 1 upon Ts, where Ts is the symbol duration. This avoid interference. This spacing also avoid the interference between the subcarriers without using any guard band. Also, all subcarriers have integer sinusoidal cycles so that when we add them upon demodulation, their sum will be 0. This condition guarantees for the symbol recoverability. If these two conditions are satisfied, then we can easily recover the symbol. So, as we have seen that using orthogonal frequency division multiplexing, we can minimizes the effect of intersymbol interference. But in orthogonal frequency division multiple access technique, maintenance of a orthogonality condition is a major challenge, and many times if a single signal on the entire bandwidth loses its orthogonality, we will not able to obtain the original transmitted sequence, and the loss of orthogonality will affect the entire bandwidth. To overcome all these problems, a new technique is introduced which is known as interleave division multiple access technique. Interleave division multiple access technique works on a different principle than that of orthogonal frequency division multiplexing and provides a much better way of communication. Basically, the concept of interleave is the main principle of interleave division multiple access system. As we know that interleaving means we will insert some pages, or we can arrange the bit in a manner so that effect of intersymbol interference is minimized. Basically, interleave division multiple access techniques are often known as next generation multiple access technique for code division multiple access and orthogonal frequency division multiple access technique. In interleave division multiple access technique, different users can use different types of interleavers, and interleavers are used to differentiate the signals on the entire bandwidth spectrum. Basically, in interleave division multiple access technique, each user use different type of interleavers, and using these interleavers, they make their information different from each other. Since each user utilizes different type of interleavers, this ensures the minimization of intersymbol interference. The interleavers works in a very specific manner, and in interleaver, the input data is organized in a matrix form. This matrix processes the data row-wise at the input and produces the output in a column-wise fashion. This is the block diagram of interleave division multiple access technique, where D1, D2, Dk represent the different symbols, and the transmitter portion of interleave division multiple access technique is the upper one, and receiver portion of interleave division multiple access technique is provided in the lower part of this figure. To demonstrate the various noise which occur during the transmission in the channel, we have considered the additive white Gaussian noise. Now, the first and very basic block of IDMA transmitter is forward error correction encoder. This encoder is used to encode the symbol which we want to transmit. After this encoding, the output is applied for spectrum spreading. Using spectrum spreading, we enhance the bandwidth of input. After spreading the spectrum, the signals are applied to interleavers. So, next block is interleaving. In interleaving block, we use different type of interleavers, and after interleaving, the signal is applied to channel. This process is applied all the symbols which the user want to transmit. After application of all these processes, the informations are combined and transmitted on the channel. At receiver end, elementary symbol estimator signal detection is the first block which estimates the symbol, and after passing through this block, we apply the signal to de-interleaver which remove the interleaving, and its output is applied to decoder. The decoder decodes the information and estimate the original transmitted symbol. The first block, as we can see, the first block at the receiving end is the elementary signal estimator block, and its main function is to estimate the interference, and it also resolve interference partially. This is the unique block in interleave division multiple access system, and it is special as it overcomes the effect of interference at the receiver's end. The same process is applied all the transmitted signal, and we will get the correct sequence from this receiver. Now, there are multiple hybrid techniques in multiple access scheme. In these techniques, our purpose is to utilize the beneficial points of different multiple access technique and combine them so that we can obtain better result and better transmission. So, when we talk about hybrid method of multiple access scheme, the first is hybrid frequency division multiple access and code division multiple access technique. In this technique, the available wide bandwidth is divided into a number of sub-spectrum with a smaller bandwidth or narrow bandwidth. After dividing the entire bandwidth into narrow bandwidth, each bandwidth uses the code division multiple access technique, and using this technique, different user can utilize the narrow band spectrum. Similarly, the next hybrid technique is hybrid direct sequence frequency hop multiple access. In this technique, a direct sequence modulated signal center frequency is made to hop periodically in a pseudo-random manner. Basically, in this kind of hybrid technique, we first use a direct sequence spread spectrum modulation technique, and after using this modulation technique, we periodically change the central frequency of the modulated signal. Next is time division, code division multiple access technique. In this, different spreading codes are assigned to different cell. Within each cell, only one user per cell is allocated a particular time slot. At any time, only one CDMA user is transmitting in each cell. Next is time division frequency hopping. In this technique, the user can hop to a new frequency at the start of new TDMA frame. Actually, in this hybrid multiple access technique, each user utilizes a new frequency only at the start of the new TDMA frame. Now, we will discuss about multi-carrier modulation technique. Actually, in digital transmission through band-limited channel causes inter-symbol interference. As I have demonstrated earlier, that when we transmit a pulse, such kind of rectangular pulse, which is limited in time, its frequency response will be like this. And when we transmit this rectangular pulse to a channel which is band limited, it will suppress the sideband of this spectrum of this rectangular pulse. Due to suppression of these side lobes, in the time domain effect will be like this. The pulse will be broad, and this causes inter-symbol interference. So, in digital transmission, inter-symbol interference is a major problem. A channel equalizer which is used at the receiver end is used to compensate the channel distortion. When we transmit any information on the such kind of band limited channel, we certainly going to face inter-symbol interference. To avoid inter-symbol interference, we use different narrow frequency subcarriers which are orthogonal to each other, and utilizing these orthogonal carriers, we can avoid inter-symbol interference. If these subcarriers are orthogonal over the simple duration, then this process is known as orthogonal frequency division multiplexing. Actually, in orthogonal frequency division multiplexing, the input data stream is converted into M symbols, and each symbol has a duration of Ts second, and each of which in turn is used to modulate parallel synchronous subcarriers. The concept is shown here. First, the incoming data sequence, which is serial like this: S1, S2, S3, S4, S5, S6, S7, S8 and S9. This serial data is converted into parallel data like this: S1, S2, S3, S4, S5, S6 and so on. After converting this serial data into parallel, each symbol is assigned with a different frequency, like S1, S2, S3 is assigned F1 frequency, S4, S5, S6 assigned F2 frequency, and these frequencies are orthogonal with each other. After applying different orthogonal frequencies, we combine them and we will get a orthogonal frequency division multiplexed signal at output. Now, the concept of orthogonality is demonstrated here. We know that when the dot product of two signals are 0, then the signals are orthogonal each other, like this. This is the condition of orthogonality in continuous time, and this is the condition for orthogonality in discrete time. Here also we can see that if we multiply these two signals, the result, and integrate over the time period, the resultant will be 0. Because for first half time duration, the product will be 1, and for rest half period, the product will be -1. And when we add them, we will get 0. This is the condition of orthogonality. So, if two signals satisfy these conditions, they are certainly orthogonal with each other. Here also the subcarrier setting is demonstrated here, like this is the frequency F1 which we have allocated for symbol S1, S2, S3, and this is the frequency for symbol S4, S5 and S6. There is a certain margin in between F1 and F2, and this margin ensures the condition of orthogonality, and this condition is equal to 1 upon Ts. This is the example of 4 subcarriers with 3 symbols per subcarrier at orthogonal frequency division multiplexer modulator stage, like the symbol S1, S2, S3 has allotted a frequency of F1, S4, S5, S6 utilizes frequency F2, S7, S8, S9 utilizes F3, and S10 to S12 utilizes F4, and these 4 frequencies are orthogonal with each other, and this condition minimizes the effect of inter-symbol interference. Here the same thing is demonstrated for S1 to S3. This is the serial data stream which we want to send using orthogonal frequency division multiplexing. So first this serial data is converted into parallel data like this: S1, S2 and S3, S4, S5 and S6, S7, S8, S9, S10, S11, S12. And now this first symbol is utilizing F1, and after F1 frequency there is a gap of delta F, and after delta time the second frequency is used, which is F2. Similarly, for this symbol sequence we are going to use F3 and F4. The symbol period and the frequency spacing are related inversely, that is, symbol duration is equal to 1 by delta F. So, to maintain the orthogonality condition, the frequency spacing between the carriers must be 1 upon symbol duration. If the modulation scheme used on the ith subcarrier can accommodate ki bits per symbol and the subcarriers are spaced by 1 upon ts hertz, where ts is the symbol duration of subcarriers, delta f must be equal to 1 upon ts. Then the duration of OFDM symbol duration must be related to symbol duration by this equation. Ts equals to n times of symbol duration in orthogonal frequency division multiplexing. By choosing n sufficiently large, the symbol interval Ts of the subcarriers can be made significantly larger than the time duration of channel time dispersion, which ensure the minimum effect of intersymbol interference. As long as we maintain time synchronization among the subcarrier, OFDM allow us to transmit a different number of bits per symbol on each subcarrier. Therefore, subcarriers that yield a high signal to noise ratio due to a lower attenuation can be modulated to carry more bit per symbol than subchannels that yield lower signal to noise ratio. To implement OFDM, we use discrete Fourier transform and inverse discrete Fourier transform. The block diagram of this implementation is shown in this figure. The data is first converted into parallel form, and using this parallel representation we use inverse discrete Fourier transform, which the symbols are converted into time domain, and this time domain signal is converted into analog form and transmitted over channel. At receiver side, the information is again converted into digital form, and with this digital form we use discrete Fourier transform to get the estimate of original transmitted signal. Although this multi-carrier modulation scheme is good, but it suffers from some drawbacks, and its major drawback is high peak to average power ratio, which represent how much the peak power exceed the average power in a signal. This high peak to signal power ratio saturate the power amplifier at the transmitted and cause intermodulation distortion in the transmitted signal. So this is the major limitation of multi-carrier modulation scheme. These are the references which I have used.